Now we're going to compute some higher order derivatives to try to show you all the different ways we can explore this topic. So let's start with a more simplistic case where we're only wanting to find the second order derivatives. And before we get there, I want to think about something. If you have two variables, then you're going to have four total second derivatives. You're going to have xx, yy, xy, yx. So that gives you four. But in the case of a third order derivative, you're going to have xxx, xxy, xxz, xyx, xyy, xyz, xzx, xzy, xzz, and then triple that. So I believe when you have that, you actually have, since you have three choices for each slot, right? The first, second, and third you can derive with respect to xyz, xyz, or xyz. You have 3 times 3 times 3, so you have 27 partial derivatives. And when you get to third order, so it gets kind of wild. It's sort of an n to the n situation. So for those of you who do computer science, order of growth, it explodes. So this is one of the reasons why we want to exploit the idea of being able to mix and match partial derivatives, because that significantly lowers the complexity of what we're dealing with. Anyway, so let's get to this. So if I get, now I'm going to abbreviate. Instead of writing fx of x and y, I'm just going to write fx. Now that's technically non-standard notation, but it'll save us a little bit in writing space. So fx, we treat x as constant, so this is 3y squared. That's 0, and this becomes 10xy squared. And so then we would get, let's get fy. So that's going to be 6xy minus 2 plus 10x squared y. Okay? So then when I get fxx, that's going to be 0, and that's going to be 10y squared. So I'm going to do fxy, but feel free to do fyx and see that it's the same exact answer. fxy, so if I take the derivative of this with respect to y, I get 6y plus 20xy. And then if I do fyy, I get 6x, that's 0, plus 10x squared. So these are different, but these were the same. And that's those second order derivatives. So let's keep going. Let's get some third order. So fx is y e to the x plus natural log of z. Fy is e to the x, and that's 0 because there's no y's in this piece. Fz, that's 0. That's a constant. Derivative of natural log is 1 over the thing, so x over c. All right, so let's start thinking about partials. Or the second partials. fxx, so that has no x's in it, so that goes to 0. This becomes y e to the x. So then fxy, there's no y here, so that goes to 0, so that's just e to the x. fxz, there's no z's here, so that's 0. So that becomes 1 over z. So that's the seconds that start with x. So then what about for y? Fyy. So we start with fy. There's no y's here, so that's actually 0. Don't have to do fyx because we already did that here. So I need to do fyz. Well, there's no z's here, so that's 0. And then fz, I don't have to do fzx because that's here. I don't have to do fzy because that's here. So I just have to do fzz. So again, x is constant, derivative of 1 over z is negative 1 over z squared. So that's our second partial. Now let's look at the third partials. Y to the x. Okay, take this with respect to y, I get e to the x. So then I would get fxxz. Well, there's no z's here, so that's 0. So then let's do it with y's. So I could do yxx, but I'm sorry. Yeah, so we start with this one. Let's move to this one. So I could do xyx, but I don't need to because I've already got it there. So I can do xyz. Well, that's 0. So that completes that one. So we need to do this one. fxzx, don't need to do that one. I already have it here. So I don't need xzy. Do I need to do xzy? No, because that has the same alphabet piece. So xzz, negative 1 over z squared. And that completes that one. So now we do this one, fyy x. Do I need to do fyyx? Yes, I do. So that's 0. fyyyy is also 0. Do I need to do fyyz? The answer is yes. Again, it's also 0. All right, now let's do this one. Do I need to do f of yzx? No, because I have the same letters here. Okay, yzy. No, I've got the same letters here. Yzz. I don't see 2 y's and a z anywhere, so yes, I need to do that. So again, that's also 0. So that one's done. And then finally, fzz. So do I need to do zzx? No. Do I need to do zzy? No. Do I need to do zzz? The answer is yes, which gives me 2x over z cubed, because the derivative of negative 1 over x squared is negative 2 times that. So it's, right, you bring down the power, negative 2 times that, negatives cancel, so you have a 2. Subtract 1 from the power, makes it negative 3, 2x over z cubed. So anyway, like I said, we were expecting 27 partial derivatives, but because of all the cancellations, it's now down to 10. So I haven't thought about what the algorithm is there for that, but I know that it significantly reduces the complexity when we eliminate the superfluous ones. And it's a lot easier to look at because you don't have to worry about all this duplication of values.